So we're going to be talking about planetary magnetospheres next couple of days. And I've got here the scales of these magnetospheres, the main big ones that I think there'll be discussions about, Mercury, Earth, Jupiter, and Saturn. And the important thing to notice is that if we use the standard scaling of what a dipole, the size of a magnetosphere, if we had just a dipole magnetic field, and then you'll see that we have a major exception here in the case of Jupiter, where we have a strong magnetic field, but it's really the hot, dense plasma disk that produces this very large magnetosphere extending well beyond the standard sort of Chapman-Ferraro distance. So it has, in fact, a bimodal distribution of 66 and 92. We'll come to this issue of the bimodal distribution at the very end of my talk. It has a rapid spin period, and it's this coupling of the rotation to the plasma via the magnetic field that provides a lot of the energy to the magnetosphere, as others will be talking about. For those of you who need a little orientation, just think of the Jupiter as 10 times roughly the size of the Earth, and everything is all scaled up accordingly. So we've been talking a lot about polar outflows, and for the Earth, the canonical number that I've been hearing about is on the order of 1 kilogram a second coming out of the polar region. There was a very important study done by Andy Nagy back in 1986, looking at outflows from Jupiter, and it came up with a number that translates to an order of 40 kilograms per second. Alex Closer, who presented yesterday on the Earth, did in fact do some important work on Saturn, where he estimated an outflow on the order of a few kilograms per second. I put this up not just because Andy Nagy has been berating me for 20 years that I never mention the polar outflows, but we really need some more work to be done on this. We have Juno arriving in 2016, flying over the poles. We will be measuring, getting pretty close to the planet over the poles. So I really urge you to take what you've been doing here at the Earth and apply it to the giant planets. There's a very ripe field for research there. Anyway, let me just show the numbers back up again. When we're talking about Jupiter, remember this 40 kilograms a second for the polar estimate. So let's think about the magnetosphere of Jupiter and what's really driving a lot of what's going on. Back in 1974, when the first meeting was being held, is around the era when ground-based astronomers were planetary astronomers were looking at the Jovian system and noticing various things. We'd known for a long time that Io was a strange moon that was causing all sorts of radio emissions, but the ground-based observations of the Io plasma torus began to show that Io spews out sodium, and later we found sulfur, and ionized sulfur forms this donut of cloud of material which glows. Here it's showing in the UV, as beautifully shown by the Cassini-UVIS instrument as it flew by, but it is this glowing big cloud of gas. It's wobbling up and down because of the 10-degree tilt of the spin axis with respect to the magnetic field, or the magnetic field with respect to the spin axis. Okay, so let's talk a little bit about the source. Io has volcanoes. It spews out sulfur dioxide. It has an atmosphere that's partly sublimation, partly geysers of gas. There's a complex interaction of the flow of the plasma past the moon that leads to a variety of processes of the plasma with these neutrals, which leads to dissociation, ionization, charge exchange, and dissociative recombination. The net result of which is to take the sulfur dioxide that comes out of the volcanoes and make big clouds of sulfur and oxygen. So the net neutral source is on the order of 1 to 3 tons per second. 1 to 3 tons per second. Now, if we think about the ions, the amount of actual local ionization is relatively small. There's a little bit of ion pickup around the sides. There's a small slug of cold material that slowly comes off, pulled off the ionosphere. But most of the ion source happens far from Io. And this is because this neutral cloud extends a long way around Io's orbit, extends not quite as far as Europa, but out towards Europa. And it's the ionization of this neutral cloud, atomic sulfur and oxygen, as well as some of the molecular species, that causes the plasma torus. There's a ratio of oxygen to sulfur of roughly, that can vary between 1 and 4. It's not strictly the factor of 2 for SO2. And what happens is that this material goes into the torus, but most of the material, sort of somewhere between 2/3 to a half, and I'll show you how this varies over time, goes out as fast neutrals, because charge exchange of locally produced, relatively slow-moving neutrals with the fast co-rotating ions leads to a fast-escaping neutral material that has been observed AU away from Io in the case of sodium. Okay. So going back to the Voyager era of my PhD thesis that I did on Voyager plasma data flying through the torus, here we have Io at about 6 RJ to give you some sense of the orientation. We have a dense region of about 2,000 per cc of material, and the plasma has an ion temperature of about 100 eV, electron temperature of about 5 eV, and this is the material that's glowing with about 2 terawatts of UV emission. And the ion composition in the bulk of the torus is dominated by this mass to charge 16, a big frustration for the plasma measurements, that the dominant species, oxygen and doubly ionized sulfur, have the same mass to charge. But what you'll see is the higher ionization states begin to dominate further out, but they begin to increase further out because of increased electron temperature further out. So our best knowledge of the Io torus and the material around there actually comes from UV spectroscopy. This is a series of, this is a movie of the torus taken in different wavelengths. So these are the dominant lines out here. You can actually see the auroral bands in here at the center. But this is a little wiggling torus on its side at these different wavelengths. And here you see, going from about 600 angstroms to 1900 is the Cassini-UVis observations. And Andrew Steffel did a PhD thesis with me on a variety of ways of analyzing these data and getting very useful information over time and space. But by analyzing all these many lines, he's able to work out the composition and the temperature, electron temperature, and so on, and how they vary in time and space. So we combine that with models of physical chemistry. We take sulfur and oxygen produced by charge exchange and by ionization. Of course, charge exchange doesn't change the number of electrons, the plasma density, but it does change the species and the energy, puts energy into the system. About 40 to 80% of the energy actually comes from this ion pickup, goes into the ions. The ions couple very quickly through to the electrons. But what we find is, to explain the emissions, we really need to add additional energy from the hot electrons. And although they're only a small percentage of the total density, less than 1%, they can tickle and excite the ions and produce a lot of the radiation. And the variations in the radiation with longitude and time and so on come from this modulation by hot electrons, probably produced, associated with the coupling between the plasma and the planet, the ionosphere of Jupiter. So what happens is that then most of the energy, in the case of Jupiter, the energy of the Io torus, the plasma comes from pickup and goes out through, via the electrons, out as radiation, UV radiation, cooling off the electrons and cooling off the ions. Okay, so we can take these physical chemistry models, we can play around with a diffusion, outward diffusion. This is motion going out through, due to flux tube interchange. You've got a source in close. The stuff is driven out mostly by centrifugal interchange and moves outwards. I'm sure Tom Hill will be talking about this. This was a lot of the work that he's been doing over the years on the Jovian system associated with that transport, but you can write it in terms of the usual diffusion coefficient for radial transport. And what you find is that it takes on the order of 100 days for the plasma to move out from 6 to, say, 9 10 RJ. So it's moving around every 10 hours, and it's taking a lot longer to go out, slowly outwards. And we see with this composition again, the higher ionization states begin to increase with distance. And this sulfur, singly ionized, decreases the distance. So let's think about Europa for a minute. I know that there's been a lot of discussion about Europa, the next moon out. There were earlier estimates of the neutral source based on some Galileo flyby data and so on. And we put this into our models. Peter Delamere and I worked on this physical chemistry model. And we threw in some oxygen out here. And what you see, it has a fairly minor effect on the radial profiles of the total density of these different ion species. And so we're talking on the order of a net total of maximum, say, 20 kilograms per second of ions. But it does make a bit of a difference in terms of temperature. This is the temperature without Europa included, and you get, for the dominant species, something like 120 EV. If you add in a local source, you can have temperatures higher further out. So there's a lot of excitement about the possibility of Europa having plumes. There was a lot of discussion at the AGU. Important paper came out by Lawrence Roth, indicating, and I'm sure Melissa will talk more about this, that suggestions from some oxygen and hydrogen emissions that may be, as seen by Hubble Space Telescope, that there could be plumes, which is very important for astrobiology. In terms of the fact this means then there's coupling between the interior ocean and the outside. Very interesting for the plasma-atmosphere interaction at Europa, which we're very keen to go off and study and send a mission to observe. But whether it's significant for the magnetosphere as a whole is not clear. But that's not the point and the importance of this. That has to do with astrobiology rather than magnetospheric physics. Okay, so let me just summarize then the difference between Io and Europa. And what we see here is there's a substantial difference in terms of scale, that the total amount of neutrals at Io is not only a factor of 10 different, but the source of neutrals is substantially more at Io, relatively small at Europa. And then if we look at the total amount of plasma, again, very small amount actually coming from Europa. But of course, it's very exciting. And so I just put this up because you're going to hear a lot about Europa being exciting, which it is. But let's keep it in perspective a little bit when it comes to the magnetosphere as a source. Let's do another quick comparison with Saturn. There will be more about Saturn later, but let's keep this in mind. There's a very interesting comparison that if we have at Jupiter this large source of neutrals and a large amount, but if we look at Enceladus, what's interesting is that at Io, it's very quickly ionized. The electron temperature is high enough to quickly remove the neutrals. They become quickly ionized, and most of the material is in the plasma. When we look at Enceladus, what we see is a relatively smaller source, but the material hangs around for a long time. Neutral-neutral collisions and charge exchange leads to a puffed-up neutral torus that has a large extent, though relatively small in amount. And that the net result is that there is a neutral-dominated torus in the case of Saturn, and a lot of loss by charge exchange. So that coupling goes largely out as fast escaping neutrals, taking the energy away out of the system entirely, rather than building up a dense plasma torus that radiates in the UV, as we have at Jupiter. So it's interesting to compare these different systems in terms of the relative importance of the neutrals versus the plasma. When we look at the Io system for Voyager 1, Voyager 2, Cassini, 2 flybys, then of course we have all of the Galileo observations as well, but since the UV instruments were particularly got some good data in these cases, it illustrates the situation where we have a range of quite a range in the amount of neutral production, and we infer the range of the plasma source, and the time scale plus the total of power emitted in the UV. What I wanted to point out is shown by these arrows here, which is that what we find is that when the plasma source goes up, the time scale for radial transport tends to go down. So it tends to go out more rapidly, and conversely, if the source goes down, it hangs around for a long time. And I think this makes sense in terms of centrifugally driven diffusion. But the net result is that you end up with a fairly modest variation in the density. So the local density tends to be a fairly constant amount. And we've used a lot of the Galileo data and looked at those carefully, and there really doesn't seem to be a big variation in the total density locally. So if we think about how this material moves out from the magnetosphere, I've taken a very simple model. This is stuff that I published with with Peter Delamy in 2011. And does that mean I have? Oh, okay. Okay. So we have material going outwards and from a cylinder. And what's interesting is this, that if you think about this at the bottom, we have here a chemistry model that gives us the mass production rate, so consistent with the UV emissions in the chemistry. We have observations of density as a function of distance, and we have observations of the scale height that comes from the temperature of the ions, and we can derive a radial outflow rate. And so we do this for a radial profile in density, so this is going from Io here out to 100 Rj, several orders of magnitude. We derive a sort of drop-off here in density, increase in temperature, asymptoting to a value of about 4 Rj thick, and what we derive is a time scale as a function of distance. And what we see is in here, things are moving out slowly, this purple line here, just a few kilometers per second, and then by the time we get to the outer magnetosphere, it's moving outwards relatively fast, in fact comparable to the local Alfvén speed. And what we find is, depending on the source here, that will move up and down. But we have more rapid outflow further out. The net result being total timescale to move from the inside to the out being weeks. Now let's think a little bit about coupling. This has been a big emphasis of this meeting, but I want to emphasize when we move out to these rotation-dominated magnetospheres, we have a rather different coupling between this system. Of course, for the Earth, we have the Dungy circulation that's so important. We have to think about rotation here, coupling of the ionosphere to the magnetosphere, but we will also need to think about the coupling of the solar wind to the magnetosphere, and I'll come to this at the end. So here we have the Dungy circulation, well described, much discussed here, but in fact this is not very important out the Jovian system. What's important there is in the equatorial plane we have material rotating around, moving around and moving outwards very slowly, though at some point it begins to, the radial outflow becomes significant, and you have these spiral outward motions beyond about 50 Rj. But what's important also is the coupling between this plasma at the equator to the planet, and this begins to break down, and the plasma begins to deviate from co-rotation. And this is a variation in a diagram first proposed by Tom Hill soon after the Voyager flyby, where we began to see co-rotation decoupling of the magnetosphere from the planet, and this decoupling could happen due to ionospheric conductivity, limitations of the conductivity to keep the plasma co-rotating, or it could be that there's very little plasma at high latitudes, and that there are substantial potential drops that develop at high latitudes with these paraelectric fields. So the plasma eventually stops talking to the planet and gets lost down the tail as plasmoids in this internally driven, rotationally driven system. Now, there is some coupling to the solar wind, and we take this diagram for the Earth, and we take the magnetic field. Instead of having upward-downward configuration, we make it more realistic and have a sideways IMF coming in, which goes over the poles. And what you end up with is a situation that has a lot of opportunity for small-scale reconnection on the boundary, a viscous-like interaction, where you do have a reconnection, but it's due to these small-scale Kelvin-Helmholtz instabilities, say, between the sheath and the magnetosphere, leading to a strong viscous boundary interaction. You can do an estimate of the amount of material that leaks in, and this is a very simple estimate that was done back by Tom Hill. If you take, say, 0.1%, then you end up with a fairly substantial amount of material interacting through the boundaries. There's some evidence of this. There are higher proton-to-heavy ratios near the boundaries, and at energetic particles, you can see that there's helium, single ionized helium rather than alpha particles. Finally, I just want to mention a very interesting development. I'm sure you're going to see some more things from Jean Gigier later for Saturn. But he showed me this cartoon, and it got me thinking about some very interesting possibilities, that on the flanks, we have these what I call chicken wings, which are these closed regions of flux that are pulled back down the tail, also observed by Poisson's models for the Earth. And what we now think is happening at Jupiter is we have these regions of closed magnetic flux on the sides. We have a lot of interactions on the boundary. Magnetic flux from the IMF indeed penetrates through here. We have some closed magnetic flux. We have material going down the tail, possibly small-scale stuff going through at the diffusive scale down the tail, reconnection here on the boundary. So this is a very different magnetosphere than we were used to thinking about, very different from the Earth. And when we look at the sideways view, you'll see there's a whole load of question marks here because we've not flown over the poles. Juno will flow over the poles, and we'll get a sense of the size of the polar cap and how things work at high latitudes. This is a very much an unknown, unexplored area, which we hope to explore over the next 5 years. Finally, I'm going to just mention a paper that's in review right now, about to come out. If you look at the solar wind out at 5AU, we see a big step in the pressure. It goes up, and then it tends to take some time to recover. We think that there's a situation at Jupiter where we have an expanded magnetosphere. It then gets compressed and then relaxes over a period of time, quite slowly over days. And if you do a simple estimate based on my model of the flow through the disk, what you find is the refilling time is hours. So as it slowly moves out over days, it refills. So it's not as if you compress it and then open it up and it's empty. As it moves out, it actually fills back up again. The consequence of this is that if we look down now on the system, we end up with some very strong shears on the dusk side, which may be related to the dusk aurora that Melissa may be talking about in the next talk. So you have compression pushing these chicken wings, down the tail, and then they come back as the magnetosphere expands, but you end up with a lot of shear on the dusk side on expansion. So I've covered a lot of material. It's a big magnetosphere. There's a lot going on here, very different from the Earth. But in terms of sources, most of the material comes from Io. There's some solar wind source. This is a crude estimate. The polar wind, we need a better number. Alex, where are you? Please go back and do that work. And Europa is relatively small. Thank you very much.
Thank you very much, Fran. So questions? Andy.
Andy, just hang on a sec. Let me get you.
My question has to do with the heavy ion observations, the Jupiter flyby of, I always get confused, New Horizons. When I last talked to Dave, he implied that they're reanalyzing that conclusion. Do you know where that stands?
Yes, he has a graduate student, George Nicolau, who's working, and I'm heavily involved in that study, reanalyzing the data. I think I know what you're after. There was a suggestion in the original science paper of H3+ in those data. I personally have some doubts about it. It's very hard to imagine that it's all the way down at 2000 RJ, but maybe we're reanalyzing data and we're looking at that. I think that will be very important as to whether or not you can get ionospheric plasma all the way down there. Yeah.
Hi, Fran. In your energy balance in the torus,
Yes.
which is interesting, evidently these hot electrons play an important role.
Yes.
Where do they come from?
Well, good question. You tell me. We don't need very many, and my answer is always an arm-waving one, that plasma physicists have no problem making waves that make hot electrons, and they wiggle about, and they easily heat up, which is a very arm-waving, I agree. But clearly, there's some coupling to the planet. The System 3, System 4 variabilities and so on suggest, and there are models that are more specific, suggesting that this is related to the alphanic coupling between the plasma and the planet. We know there are alphane waves going back and forth coupling, and we know that there is heating of the electrons associated with that. So I think there are plenty of ways of explaining it, but which one is correct isn't clear yet.
Yeah, concerning the comparison between Io and Enceladus as plasma sources, might be worth mentioning a study by Vytenis Vassiliounis 2 or 3 years ago, maybe even more, where he put those plasma source rates in dimensionless form. To make a long story short, estimating how important they were given the dimensions and the properties of the magnetosphere that they were in, and found that Enceladus within Saturn's magnetosphere is actually equally powerful, if not more powerful, than Io in Jupiter's magnetosphere, in spite of the fact that it's considerably smaller when expressed in physical units.
Right. And yes, I'm fully aware of that study, and I think it's an interesting way of doing things, but I think he misses out a lot of there's a lot in the physical chemistry that he's ignoring, right? So, I think it's a bit of an oversimplification. But yeah, it's important. Of course, Enceladus is important.